In the last video, we laid the groundwork for quantum intuition, and now we'll back that up with the necessary math. In order to represent the state of a system or particle, especially for spin, we have to use Ket vectors. Ket vectors are complex vectors, while normal vectors have components with magnitudes of real numbers, like this. Ket vectors have complex components. They can be real, imaginary, or both. From now on, regular ordinary vectors will be called 3 vectors to avoid confusion. So for a complex component, we might say this is 3 plus 7i, and this is 2 plus 4i. And that might not make sense with the axes, but just wait a second. Now the space in which these vectors live is called a Hilbert space. So that's what the axes are part of. Hilbert spaces can have any number of dimensions, from 1 to infinity, and have axes with complex numbers on them. The particular dimensions of each Hilbert space depend on the experiment we're doing. So we'll, let's say, choose one with 2 axes, or 3, depending on how many degrees of freedom are in our experiment. For the most part, the rules governing Ket vectors are the same for 3 vectors, except that complex numbers can be used here, and they can't be used here. Now, to label the components of Ket vectors, we use vertical matrices. All the usual math of matrices applies here as well. So let's say this vector right here would have a vertical matrix. The first component, which we'll say is 2 plus 4i, would go in the first entry at the top. And then the second component would go in the second entry. So this matrix is equivalent to this vector, just like this horizontal matrix is with the proper brackets is equivalent to this real vector, this 3 vector. Now we can take the complex conjugate of scalars just by switching the sign of imaginary components, like this. The complex conjugate of 3 plus 4i would be 3 minus 4i. Ket vectors have a similar property, bras. A bra vector is, loosely speaking, the complex conjugate of its respective Ket vector, and vice versa, but it's a little more complicated than that. To find the matrix formation of a bra vector, we take the complex conjugate of every component in the Ket vector, and then switch every component across the diagonal of it. So like this. For this Ket, what we would do is first, let's write it down. We want to find the bra vector for this Ket. We would write Ket vectors like this. Let's say this Ket vector, we'll call it Ket vector k. That's how we write Ket vectors. That's the notation. This is the name, which we'll just represent with some symbol, and then we put these specific brackets around it. This is a Ket. So we can represent it as this matrix. To find the bra version, we would write it like this. This is the bra version of the Ket vector k. We just switch the brackets. It would be like this. First of all, these would be complex conjugated. So this would become 2 minus 4i. This would become 3 minus 7i. But then we need to flip them around the horizontal. And that's a little tricky with a vertical matrix, but here's how you do it. Vertical matrices start out going down like this. Now, the diagonal would look like that. So to flip them over the diagonal, we would flip them like this, which would become something like this. So it just becomes a horizontal vector. So now this would be a horizontal vector. the first component here would be the first component here, but we have to use the complex conjugate, so it would be 2 minus 4i. And then the next term would be 3 minus, you gotta remember the complex conjugate, 7i. This would be the bra version of the ket vector k. Now, this form of a vector, or any matrix in quantum mechanics, where you take the complex conjugate and then flip across the diagonal, is called a Hermitian conjugate, and that's why it's not simply a complex conjugate. A complex conjugate would just involve negating the imaginary terms like we did here, but the Hermitian has to be flipped, and there's a specific reason for that we'll see later. Otherwise, the math would not work out. Okay, now we're going to move on. So with regular vectors, we can do something called taking a dot product. We can multiply two vectors to find a scalar, which is sort of like taking the components of each and lining them up and finding the total scalar value of it. Unsurprisingly, the same thing holds true for kets and bras, except it's called the inner product and looks like this. We can take the inner product of the bra, let's say alpha, with the ket beta, like that. We just combine the two. To calculate this final scalar value, we simply use matrix multiplication between the horizontal bra vector. It's horizontal because remember we switched it across the diagonal. So that would look like this. We'd start it. First matrix, let's say, just make something up. 1, 2. That's the ket alpha. And then the vertical ket vector, which would look like this, say 3, 4, that's the ket beta. And we use matrix multiplication to find this. So let's say it'd be, if you don't know matrix multiplication, look it up, but essentially what we're going to do is we're going to multiply this term by this term, which would be 3, and then add to it this term multiplied by this term. So that would be 2 times 4 is 8, which would give us a final answer of 11. So this is essentially the same rule as for dot products. You take the corresponding components of each vector, multiply them, and then add those products together. So this would be now those two multiplying the x components, multiplying the y components, and then adding those two, as you would in a dot product. This is just the analogy of it for quantum mechanics. The reason that they're called bras and kets, by the way, is because when you take this inner product, it reads bra, ket, like bracket. And you can thank Paul Dirac for that. Alright, so there are also special types of ket vectors. For instance, a normalized vector is special in that the inner product with its own bra is 1. Let's call this ket vector n. Doesn't matter what way it's pointing, it's just that it's normalized, which essentially means that it has a length of 1. That's the most intuitive way to think of it. But again, this is in a Hilbert space, so it's not exactly a length of 1. But anyway, it would look like this. A normalized vector, a normalized ket vector, let's say n, if you take the inner product with itself, like that, whatever the components are, you would have to get 1 as your answer. So clearly, these aren't the same vector, but if they were, they would not be normalized. Also, two vectors are orthogonal if their inner product is 0. Again, the more intuitive interpretation of this is that the vectors are perpendicular to each other, but that's kind of hard to visualize in a Hilbert space because the axes are weird. So that would be like this. Let's say vector gamma, bra vector gamma, and ket vector, let's say ket vector delta. If we take the inner product of those two and it pops out as 0, that means that those two are orthogonal. They're perpendicular in the Hilbert space. And this kind of works with dot products too. If you take the dot product with a 3 vector, a real vector of length 1, it'll spit out 1. If you take the dot product of 2 perpendicular vectors in real space, it'll pop out as 0. So it still works like that. Okay, finally we're going to talk about components. There are no x, y, and z axes in the Hilbert space. That wouldn't make any sense. Instead, the components are a little trickier. They change from problem to problem. But for now, we'll just show you what the most useful way to set them up is. So you start with an orthonormal basis. This is just a bunch of vectors that are all length 1 and perpendicular to each other. It's kind of like the base vectors I, j, and k in real space, but they're different. We can set them up in a different way. And again, length 1 and perpendicular doesn't work in Hilbert spaces, but it's a good interpretation. So again, orthonormal. They're all perpendicular and they're all length 1, just like these guys in real space. This setup is useful because it gives us complex numbers to work with and more than 3 dimensions, but we can still use the basis. Okay, so within this system, every ket can be shown as a sum of the basis vectors multiplied by their different components. So like with the original 3 vector at the beginning, I think it was something like this, 4 and 3. Now, we would use our orthonormal basis in the real world as this is I, unit length 1 on the x-axis, and j, unit length vector on the y-axis. So essentially what this is saying is this vector, let's just call it v. In the real world, this v vector would be the same as saying 3, its x component, times the basis vector for x, I, plus 4, its y component, times the basis vector for y, which is j. That's a way to represent it. And we can do the same thing in a Hilbert space. Let's say that we just have some weird random set of basis vectors. This isn't how you use the notation, but it's just good to show. Let's just say A, B, and C. Let's say this is for the Hilbert space. These are the basis vectors. Let's say we can represent, let's take that out actually. It's not going to be helpful. We can just use 2 in this case. Let's say we just have 2 orthonormal basis vectors for this complex vector. How would we represent, let's say alpha up here? Alpha is 1, 2. Well, let's say the ket form of alpha in matrix form is 1, 2. But we can also represent it as 1 times A plus 2 times B, or A plus 2B. Now again, these aren't exactly the same as it would be in the real form. It would actually, the basis vectors would actually look like ket vectors themselves, like that, A plus 2B. That's the proper notation. But this is just to show you that it's almost exactly the same as in the real world. Alright, finally, we're going to talk about how to find these components if you just have a vector given to you that you just know it's somewhere, pointing some way, somewhere in this Hilbert space, and you want to find, okay, what are the components along this axis, this axis, and this axis. Alright, but it's a little tricky, so we'll do our best here. Alright, let's try to find the component in the direction of the basis vector j. Okay, so we have some Hilbert space, some vector, let's call it capital A, this ket vector. And we want to find its component along the j-axis. So this orthonormal vector is called j along this axis right here. Alright, so in essence we want to find the component of A on j. So here's what we do. We take the inner product of j with A. This is what I was talking about with the components. Dot products essentially find sort of like the shadow. It's just how much of this component of this A vector aligns with j. That's what a dot product does. So we're going to do the same thing except with a Hilbert space. We're going to find the inner product. Since we multiply similar components and then add, a lot of canceling occurs because every component of A that isn't along the j-axis just multiply by 0. Because you can think of this j as something like this. Its ket vector would be 0, 0, 0, 0, until you get to the j part, when it's 1, and 0, 0, 0, 0. That's its ket form. All these are other axes. You know, it has 0 component along the I axis, A axis, G axis, whatever, all these different. The only place it has a component is along the J axis. And because of that, whenever you multiply these terms by their like terms in A, like you do for the inner product, they cancel every time except for 1, except for on the J axis. So essentially what you're doing is 0, 0, 0, 0, 1, 0, 0, 0, 0, multiply by something, 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 the j component of A, which is in the same respective place as the 1 is, something, something, something. All these other somethings cancel out because they're multiplied by zeros in that inner product. The only thing that's left is the j component of A, which is multiplied by 1. So you get A, j. So that's how you do it. Because of that canceling, all you need to do to find a component along some axis, j, is take the inner product with the basis first, this basis vector j along this j-axis, unit length 1. So once you do that, you get the component. Another way we can represent this is that, let's call this actually alpha j, that way it won't get as confusing. So components are alpha, the vector itself is A. So, like before when we said that we can add up the components multiplied by their basis vectors to find the vector itself, which is, you know, component times basis vector, add them, you get the final vector. We can do the same thing with this A vector we have, A ket vector. What we can do is A is alpha 1 basis vector 1. Just for the first axis that we were talking about. Plus alpha 2 basis vector 2, the second axis. Keep going, and you get the final vector A. Just like we said that real vector is 3i plus 4j. So if we want to show this in a more compact form and keep this j that we like, I hope you're going to get the sum over all possible values of j, that's what this means, out of every possible value of j, whatever this term is, alpha j times the basis vector j. That's one way to represent any ket vector you want in the basis terms. Alright, so this will become more important later, but just for now, it shows you how you can add up components to find basis vectors. Alright, next time we're going to show you how these ket and bra vectors can be used to calculate measurements for spin that we talked about last time. Bye!